EEG AI sleep decoder for early detection of neurodegenerative disease and dream visualization by Sihhyun and Fatima Boud, team number 7. So both Alzheimer's and Parkinson's diseases are very devastating. But why? It's mainly because the symptoms appear. The brain has already undergone irreversible damage. So the recent researchers highlight a promising clue, which show changes in the REM sleep, especially REM sleep behavior disorder or RBD. It may show up years before traditional symptoms. So unfortunately, current detection methods like PET scans or fMRIs and cerebrospinal fluid analysis are expensive, invasive, and only used after symptoms appear. So even dream decoding has been explored using fMRI with GANs, but that's only in research labs. So it's very impractical for daily personal use. Here we are proposing a smarter solution, a wearable EEG-based AI system that can do both. It can detect early brain risks, but can also visualize symbolic dreams. Over 55 million people are affected by Alzheimer's and Parkinson's and other neurodegenerative diseases. Early detection could change everything, showing decline, preserving function, and improving quality of life. But right now, tools like polysomnography are costly and not scalable. Meanwhile, wearable EEG headbands are affordable but lack diagnostic depth. So what we want to do here is to build the first system that is affordable, non-invasive, home usable, personally engaging. So brain health is really urgent and the current tools are out of reach. It's time for a breakthrough. Our goal is to create a dual function EEG platform. So first, we want to detect the REM anomalies linked to early neurodegenerative risk, especially Parkinson's. Second, we want to reconstruct the symbolic dream imagery from EEG data to make the experience engaging and meaningful. So this isn't just a medical tool, it's a consumer friendly and it's a neuroscience-backed platform for brain wellness and early diagnosis and self-discovery. So to break our goal down into 4 specific aims, we have 1. Develop a REM learning model to detect REM sleep anomalies from EEG signals. Aim 2 is to build a generative AI model that transforms EEG features into symbolic dream images. Aim 3 is to integrate both into a wearable device using consumer-grade EEG hardware. And Aim 4 is to test the system in real-world setting to evaluate usability, engagement, and diagnostic accuracy. As for the approach, here's how we will do it. First, we collect the data. We will recruit healthy and high-risk participants using wearable EEG headbands and during sleep. And we also will collect the EEG signals, automated sleep staging, and self-reported dream description. Second, we will train the model by training a REM anomaly detection model using labeled REM data, and then train a dream visualization model using EEG features paired with symbolic dream labels. And 3 is the evaluation. So for the REM detection, we'll use metrics like the AUC and the accuracy, sensitivity, and specificity. For dream visuals, user surveys and image text clip scores and GPT-based semantic evaluation will be used.
Our first step is data collection, which builds the foundation for both our diagnostic and generative models. We'll recruit 2 groups of participants, healthy individuals and high-risk subjects such as those with known REM sleep behavior disorder or a family history of neurodegenerative disease. For hardware, we are using consumer-grade wearable EEG device like the Dream or Muse S headbands. These devices are non-invasive, can be used at home overnight, and provide high-resolution multi-channel EEG signals. Each night, we'll collect 3 key types of data. Low EEG time series, which forms the input for both models. automated sleep staging. It can segment sleep into REM, NREM, and wake, and self-report dreams descriptions recorded in the morning after sleep. We'll then process the sleep staging using the tools like MD5031 and embedded dream text into semantic vector space using GPT or CLIP to align them with symbolic imagery for training the dream visualization model. Together, this dataset allows us to map between neural signals, physiological sleep stages, and subjective experience, a truly multimodal approach. After collecting each and sleep data, we move to the heart of our system, model training. For the REM anomaly detection model, we'll input multi-channel EEG signals, apply pre-processing techniques like filtering and normalization, and feed the data into a deep learning model. We can consider architectures like CNN-LSTM hybrid or even transformer-based time series encoders, which are ideal for capturing temporal EEG features. These models will classify whether REM episodes contain abnormalities linked to neurodegenerative risk, training using binary cross entropy rules. On the other hand, the dream visualization model is generative. It maps EEG features during REM to symbolic dream representation using a latent diffusion model. It is similar to models like stable diffusion, but adapted for each input. Instead of literal images, the training target will be semantic concepts derived from user dream reports such as flying or water. These are embedded into a latent space using CLIP or GPT embeddings for cross-model alignment. Each model is trained separately, but ultimately both will be merged into a single wearable system. As we develop the system, validating our model is critical to ensure real-world usability and medical relevance. For REM anomaly detection, we will use standard diagnostic metrics like accuracy, sensitivity, and specificity. This will be benchmarked against polysomnography annotations, the gold standard in sleep analysis. For dream visualization, things are more complex. Since dream content is subjective, we'll evaluate output on a symbolic level. So we will use CLIP scores to assess image text alignment, GPT-based semantic parsing to match predict content with user descriptions, and collect user ratings on how well the visual reflect their actual dreams. By combining both objective metrics and subjective feedback, we ensure our models are both scientifically sound and personally engaged. Of course, there are challenges. First, dream reports are subjective. So instead of literal sense, we will focus on symbolic dream concepts like flying, water, or conflict. And second, generate images might be hard to interpret. To improve understanding, we will use GPT-based semantic parsers that translate each output into keywords or themes. If successful, this platform will have massive impact. In the medical field, it enables earlier intervention for Alzheimer's and Parkinson's disease. In the science field, it can advance brain decoding and sleep neuroscience. Consumers make dream analysis and brain health accessible and fun. With your support, we can turn sleep into a window for early diagnosis and inner exploration. This is the EEG sleep decoder. Detect early, visualize deeply, sleep smarter.